Hi students. Okay, today we are learning the topic is in the singly variable calculus, the first theorem, Rolle's theorem. Okay, in this lecture we discussing what is statement of Rolle's theorem and geometrically explanation of the Rolle's theorem and some problems on Rolle's theorem. Okay, first of all see the statement. Let f from closed interval a comma b tends to or be a function such that it is continuous in closed interval a comma b, it is differentiable in open interval a comma b, and f of a is equal to f of b. Then there exists at least one point c is belongs to open interval a comma b such that f dash of c is equal to 0, and that is a given function f of x is continuous and differentiable, and that function యొక్క second ordinate, that is f of a and f of b both are equal. Then we have to find out at least one point between a and b. At least means maybe more than one points also exist such that at that point the derivative is equal to 0. This is the statement of Rolle's theorem. So see that here. So that is another statement of Rolle's theorem. So let f from closed interval a comma b, a comma a plus ah tends to or be a function such that it is continuous in closed interval a comma a plus h, it is differentiable a comma a plus h, and f of a is equal to f of a plus h. Then there exists a real number theta is belongs to open interval 0 comma 1 such that f dash of a plus theta h is equal to 0. And in the first statement b a comma b, but here a comma a plus replacing b by a plus h. H is the least positive integer near to, that is a comma a plus h is the both are nearly same value, and then there exists here finding the theta value. So theta is a real number between 0 to 1, there is a negligible theta value, then such that f dash of a plus theta h is equal to 0. This is the another statement of Rolle's theorem. So see the next one. So geometrically interpretation of Rolle's theorem. So how to explain the geometrically of the Rolle's theorem? See that first of all, if the function f of x satisfying all conditions of Rolle's theorem. So all conditions means that function is continuous and differentiable and f of a is equal to f of b. So that is equal to here by geometrically. So first condition, the function is continuous, that means the curve y is equal to f of x is continuously curved from the point a of a comma f of a to b of b comma f of b on the curve. This is a continuous curve from a to b. So that is equal, see that here. Let the y is equal to f of x is a curve. This is a graph of y is equal to f of x defined from a to b. So here point is a comma f of a, b comma f of b. అవునా, ఇక్కడ x కోఆర్డినేట్ a, y కోఆర్డినేట్ f of a, x కోఆర్డినేట్ b, y కోఆర్డినేట్ f of b. So see that this is from a to b is a continuous curve and there is no breaking from a to b. Second one is differentiable. So differentiable means the geometrically there exists a unique tangent to at every point on the curve y is equal to f of x between the points a and b. And from a to b at every point there exists a unique tangent, that is a differentiable function. Okay, next third one, f of a is equal to f of b, that is equal to f of a y ordinates and second point y ordinate b f of b both are equal, and here point is the same and the same single line here. This is the same, f of a and f of b both are same. So this is the three conditions are satisfied. Then there exists at least one point c on the curve y is equal to f of x between a and b where the tangent is parallel to the x-axis. This is a geometrical is at that point the tangent is parallel to the x-axis because see that this is a tangent line. So tangent at the point C, that is the slope is f dash of C, f dash of C, which is parallel to the x-axis. X-axis slope 0. They both are parallel, that is equal to f dash of C is equal to 0. So where C is between A and B. So this is the geometrical interpretation of the Rolle's theorem. Is that clear? So see the next now verification of Rolle's theorem. Okay. Yeah, first example. Verify Rolle's theorem for f of x is equal to x plus 2 whole cube into x minus 3 whole power 4 in closed interval minus 2 comma 3. So when you say that Rolle's theorem is applicable for the given function must to be satisfies the three conditions, that is the continuous, differentiable and f of a is equal to f of p. So this is a given function is a polynomial of degree 7. We know that every polynomial is continuous and differentiable in R. So therefore clearly which is continuous and differentiable in closed interval minus 2 comma 3. Next third condition and finding the differentiation. So differentiation finding here f dash of x. So this is u into v method. So 3 into x plus 2 whole square into x minus 3 whole power 4 plus x plus 2 whole cube into 4 into x minus 3 whole cube. That is equal, we have to common here x plus 2 whole square into x minus 3 whole cube common. So remaining here 3 into x minus 3 plus 4 into x plus 2. Simplification is x plus 2 whole square into x minus 3 whole cube into 7x minus 1. Okay, now observing here in the given interval f dash of x is defined, that is exist at every point x between minus 2 comma 3. So that is the exist. So next third condition f of a is equal f of b. So f of a and f of a is equal minus 2. F of minus 2 is equal 0. F of 3 is equal 0. Therefore f of minus 2 is equal to f of 3 equal. So three conditions are satisfied. Okay, Rolle's theorem is applicable for the given function in the interval. So that is applicable. Now verification. So what is the verification means? To finding the at least one point C between minus 2 comma 3 such that f dash of C is equal to 0. That is equal to here f dash of x already find out. So here substituting C. So that is equal C plus 2 whole square C minus 3 whole cube into 7C minus 1 is equal 0. So that is equal 7C minus 1 is equal 0. So C is not equal to minus 2, C is not equal to 3 because C is a between but not minus 2, 3. So 7C minus 1 is equal to 0. C is equal to 1 by 7. So 1 by 7 is belongs to in the interval minus 2 comma 3. So there exists one point between minus 2 comma 3. Therefore Rolle's theorem is verified. Okay, clear, understood? See the next example here. So discuss the applicability of Rolle's theorem for f of x is equal to x square plus 1, that is 0 less than or equal to x less than or equal to 1, 3 minus x 1 less than or equal to x less than or equal to 2 in the interval 0 comma 2. So that is equal to given function is, so the clearly it's continuous and from 0 to 1, 1 to 2, there is no breaking from 0 to 2. So clearly it's continuous. So it's continuous in the interval 0 comma 2. Now discussing the differentiability. So at x is equal 1, here breaking point x is equal 1. Now differentiable is or not. X is equal 1 here, left derivable L f dash of 1 is equal to limit extends to 1 minus f of x minus 1 by x minus 1. So left derivable means left point, f of x is equal to x less than 1. X less than 1 is equal to f of x square plus 1. So this is x square plus 1. F of 1 is equal to 2 by x minus 1. That is simplification is limit x tends to 1, x square minus 1 by x minus 1. So this is x square minus 1 means x plus 1 into x minus 1. X minus 1 is a cancel, x plus 1. So that is equal to left derivable is 1 plus 1 is equal to 2. 2 is the left derivable at x is equal to 1. Next right derivable at x is equal to 1. Limit x tends to 1 plus f of x minus 1 minus f of 1 by x minus 1. So x greater than 1. When x greater than 1, f of x is equal to 3 minus x. So that is a 3 minus x minus 2 by x minus 1. Simplification is limit x tends to 1 minus x plus 1 by x minus 1. So here minus common, x minus 1 is a cancel, that is a minus 1. That is a minus 1. So minus 1 is the right derivable. Both are not equal. Left derivable is not equal to right derivable. So therefore given function is not differentiable at x is equal to 1. At x is equal to 1, 1 is belongs to given interval here. So that is equal to is not derivable in the interval 0, 2. So that is the second condition is not satisfied. Therefore Rolle's theorem is not applicable in the given interval 0, 2. Okay. See the next example. Verify Rolle's theorem for f of x is equal to 1 plus x power 2 by 3 in closed interval minus 4, 1. So that is equal to given function 1 plus x power 2 by 3. So clearly which is continuous because there is no breaking point between minus 1, 4 is a continuously curve. So next one, finding the differentiation. So derivative of 1 0 plus derivative of x power 2 by 3 into x power minus 1 by 3. So x power minus 1 by 3 can be written in the denominator, 2 by 3 into 1 by x power 1 by 3. Observing here 1 by x power 1 by 3. So this is exists at everywhere except to 0. But except to 0 means 0 is must be in the given interval. So therefore f dash of x does not exist at x is equal to 0. That 0 is belongs to given interval. So therefore that is a not derivable at x is equal to 0. So that is a given point is belongs to the given interval. So therefore given function f of x not derivable in minus 4, 1. Therefore Rolle's theorem is not applicable in closed interval minus 4, 1. Okay. See the next example. So verify Rolle's theorem for f of x is equal to e power x into sin x minus cos x in closed interval 5 by 4, 5 by 4. So that is equal to here. So given function is, so clearly it's continuous and differentiable because e power x is the exponential function, is always continuous and differentiable. Sin x, cos x both are continuous and differentiable. Therefore product of the two functions is also continuous and differentiable in the given interval. Okay. So now finding the differentiation. So differentiation is equal to f dash of x is equal to, it is a u into v method, e power x into sin x plus, so sin x derivative cos x plus cos x derivative minus sin x, that is the sin x plus e power x derivative e power x into sin x minus cos x is equal to here. So cos x is a cancel. So remaining 2 into e power x sin x. This is f dash of x is always exist in the given interval. But for any value between minus 5 by 4, 5 by 4 is existent. So there is a differentiable. Next condition verified, f of a and f of b. So f of a is equal to 5 by 4. F of 5 by 4 is equal to e power 5 by 4 into sin 5 by 4 minus cos 5 by 4 is equal to 0. So next f of 5 by 4 is equal to e power 5 by 4 into sin 5 by 4 minus cos 5 by 4. Both are values equal together. 1 by root 2 or 1 by root 2, that is equal to 0. So both are equal. F of A is equal to F of B. That is f of 5 by 4 is equal to f of 5 by 4. So therefore Rolle's theorem is applicable for given f of x in the interval 5 by 4 comma 5 by 4. Now verification to find any c between 5 by 4 comma 5 by 4 such that f dash of c is equal to 0. Already finding f dash of x is equal to 2 into e power x sin x. That is equal to 2 into e power c sin c is equal to 0. But e power c is not equal to 0. Then sin c is equal to 0. But sin c 0 when in the sign? Only sin n pi. N pi be, but choosing the given interval 5 by 4 comma 5 by 4. That is equal, exist one point is pi. That is sin n pi. Therefore c is equal to 5. 5 is a must be belongs in pi by 4 comma 5 by 4. Therefore Rolle's theorem is verified. Okay, is it clear? Yeah, thank you. This is a Rolle's theorem and its problems and verification. Thank you. For more videos, please do subscribe my channel, like and share it. Thank you.